Okay, so I wanted to review sort of the concept of a supernode. This is a circuit that at least my section had looked at in recitation recently, and I wanted to analyze it, use it as an example. But before I do that, what I'd like to do is first just kind of refresh ourselves about the differences between nodal analysis and mesh current analysis, because that really does help to understand how the supernode sort of idea works. So anytime I have a circuit like this, right, I can use a couple of different approaches to study it. If I use nodal analysis, right, nodal analysis, which is what we're going to use here. When I do nodal analysis, what I'm doing is I am solving for node voltages, okay? Which basically means that I'm solving for voltages at some point in the circuit with respect to ground, okay? All right, voltage is always defined between 2 points. So if I'm solving for the voltage at some point in the circuit, I need to say that that point in the circuit is some voltage above some other point. And so we define some point called ground. Now, to do this, to solve for the node voltages, we essentially write KCL equations. KCL equations for the currents at each node, okay? All right, so in other words, when you write your KCL equations, when you do nodal analysis, you're writing KCL equations. Your KCL equations better all have currents. In other words, every term in those KCL equations better be a current. And that's something you want to verify to make sure that your equations are correct, okay? If I do mesh analysis, on the other hand, in mesh analysis, I'm solving for mesh currents. And when I do that, I write KVL equations, okay? So those KVL equations better all have voltages in them. In other words, every term in my KVL equations better be in terms of a voltage. If I have something in terms of a current, my mesh analysis is totally wrong. The problems that you run into, so with nodal analysis, I run into a problem when I have voltage sources. Okay? And with mesh analysis, I run into a problem when I have current sources. Okay? Why do I have a problem with voltage sources when I do nodal analysis? Well, remember, when I do nodal analysis, I'm writing KCL equations for the currents at each node. The problem I run into is that when I have a voltage source, for a voltage source, there is no way to define the current through a voltage source, right? As I talked about this previously in one of my other videos, I said if I look at the IV characteristics of a voltage source, so in other words, maybe this 12-volt source that I've got right here, VI, all right? What I can see is that this voltage source always has 12 volts across it, no matter what current flows through it. So there's no way for me to know the voltage across this thing and then somehow be able to define what the current is. It's just impossible. If I look at a resistor, on the other hand, if I know the current through that resistor, that current is directly related to the voltage across that resistor. Similarly, for a current source, in mesh analysis, I've got the problem of here's V and here's I, right? Let's say I had a 12 amp source. Well, I know exactly what the current is through that element, but I have absolutely no idea what the voltage is. In other words, there's no way to define a relationship between I and V and a current source, and there's no way to define a relationship between I and V and a voltage source. Those two things are problematic. So I got to be careful with basically what that means. So when I get something like I have in this circuit right here, where I have a supernode, I have no way of defining the current through this 12-volt source. Okay. I do have a way based on my equations, my KCL equations, but there is no direct relationship that I know about voltage sources that allows me to relate that voltage across this guy to the current through him in the same way that I do for a resistor. Okay, so let's look at this particular circuit as an example. Okay, now in the book, this is an example in your textbook. All right. They ask us to find the voltage V0. All right. So find V0 using Thevenin's theorem. Now, we're going to do that. All right. And I suggest you look at the video on Thevenin equivalence if you want to kind of understand a little bit more about that. But in this particular case, to use Thevenin's theorem, what I want to do is I want to break the circuit right here at those terminals A, B. Okay? And I want to view this guy and say that everything to the left of the line AB is some network. And then I'm going to hook two 1K ohm resistors across here. And I want to solve for the voltage VO across there. So what we said previously is, well, to be able to, so again, if you watch that video, it goes through that pretty carefully. As long as I create a circuit model for what's inside this box that is completely equivalent to what is inside this box, then I can use Thevenin's theorem. So the idea is for two circuits to be equivalent, it has to be the case that the VI relationship at those terminals, so the VI relationship here, better be exactly the same for the equivalent circuit as it is for the actual circuit. All right? As long as that's true, then those two networks are completely identical from the perspective of the terminals, and I can use the simplified model. So watch the video on that if you want to understand it. All right, now, if that's the case, and I break this circuit here, and I want to use Thevenin's theorem, I said to the left of the terminals AB, the circuit looks like this. All right, I have 2000 IX. I have a 1 kilo ohm resistor. Okay. I have a 2 kilo ohm resistor. Okay. I have a 12 volt source. And I have another 2 kilo ohm resistor. Now, right, there's the terminal right there. All right, so this guy basically would be V and I. So in other words, I want to get the equivalent circuit that has the same terminal characteristics as the original network. So that means I need to get my V open circuit, and I need to get my Thevenin equivalent resistance. Okay. So all right, how do I approach that? In this case, simplest way to probably figure out my open circuit voltage is to say, well, if I is equal to 0, okay, so let's say I is equal to 0, then the voltage V right here is the open circuit. Okay. So let's call this ground. I want to use nodal analysis to try to figure out what that V open circuit is. So in this case, what I'm going to do is I'm going to call this node 1, and I'm going to say this has a voltage V1 with respect to ground, and call this guy node 2 and say that it has a node voltage V2 with respect to ground. And so in this case, I see that V2 is equal to that open circuit voltage, right? Whatever the node voltage is here, is the same as the voltage across this 2K. That's the open circuit voltage when no current's flowing out of here. Okay? All right. So what do I do? If I want to do my nodal analysis, I have to write my KCL equations. So I'm going to call this guy here V1K. Call this branch current I1K. Call this branch current I2K. This guy was defined to me previously as IX. Okay, like that. All right. So let's write our KCL. So the way when I do nodal analysis, I start with my KCL. So I say KCL at node 1. Okay. So essentially what that is my I1K, which is the current coming through that 1K resistor, is equal to I2K. Now, I got to be careful about this because there's also a current going through this 12-volt source. So I'm going to call that guy IT. All right, I don't know what he is. I'm going to call him IT. So I'm going to write this as the current through this 1K resistor is equal to I2K plus IT. All right, that's just a true statement. Now, I know that I1K is equal to V1K, the voltage across that 1K resistor, divided by 1,000 ohms. All right, this here is just Ohm's law. And the I2K is basically V1, the voltage across that guy, divided by 2K. Now, if I look at IT, I don't have any way to define anything about IT, right? IT is the current flowing through this 12-volt source. There is no clear relationship between the current through a voltage source and the voltage across it, okay? So that's all I can do. I have to stop there. Now notice this guy is volts over ohms, which is amps. This is volts over ohms, which is amps. And this guy is amps. So my units check. Every term in here is a current. Now I have to do a KCL at node 2. Okay, this one's a little more straightforward. I have IT, the current flowing through this 12-volt source, has to equal IX. Now IX, all right, IX is the current through this 2K, so that must simply be V2 divided by 2,000. Okay? All right, now what I can see right away is I have two equations here. Okay? So this equation and this equation, and I ultimately have a couple of unknowns, right? So I need to work on simplifying that down. One important thing right here is I can take this equation right here, my KCL at node 2, and I can bring it into my KCL at node 1. All right? The reason I can bring it in there is here's the important thing about a supernode. So in this case, I got this supernode. What I can see is whatever current flows through this 12-volt source must then flow out of it. So in this case, whatever flows into it here at node 1 leaves it at node 2. Okay? So the definition that we make is I can say with a supernode, and this is the way I look at it, is I can say, well, whatever current enters this guy goes this way and this way. In this particular case, it can only go in one pathway because this guy is open circuited. All right? So what I do is I then take these two equations and combine them. So I get my V1K over 1,000. V1K over 1,000. I gotta clean that up. My V1K over 1,000 equals V1 over 2,000. And I can say, all right, plus IT, well, I can bring in IT and say this is V2 over 2000, like that. All right, so now I've partly simplified this guy. Now the one thing I can say is I can say, okay, well V1K, I can write that in terms of what I know in terms of the existing node voltages. So V1K, if I look carefully and do a KVL, so by KVL, so if I do a KVL around this loop right here, I can see that the voltage at the plus terminal of the 1K resistor is negative 2000 IX. So in other words, this guy right here is a dependent source. He's a voltage dependent, or he's a voltage source that depends on a current. All right. So the voltage right here with respect to ground is negative 2000, and the voltage here with respect to ground is V1. So I say the voltage at the plus terminal minus the voltage at the negative terminal. All right. So I plug that in over here. So I get negative 2000 IX minus V1 over 1000 equals V1 over 2000 plus V2 over 2000. All right. So now I have, looks like a couple of unknowns still, although the thing I can do here is, so I've got this IX, all right. I also know that IX is equal to V2 over 2000, so I can plug this guy in here again, all right, and sort of rearrange everything. So I can write this as, let's see, V1 over 2000 plus V1 over 1000 plus V2 over 2000, like that. And over on this side, I have minus 2 times IX. And I can rewrite that as minus 2 times, so IX I said was V2 over 2000. Right, that's plugging in this guy. All right, equals all of that. All right, I don't feel like rewriting it. If I rearrange everything, I get that 0 equals V1. I'm going to write it like this. It's 1 over 2000 plus 1 over 1000. I don't feel like simplifying that. I feel like my likelihood of making a mistake goes up if I try to simplify it, so I don't. All right, plus V2 times 1 over 2000. And the 2 over 2000, I guess I'll simplify that down as 1 over 1000. Like that. So now I've got one equation and two unknowns. Now there's another equation I can write because I know by KVL in this particular case. So I need to get my other equation. If I look at this guy, I can look at this circuit and I can say by KVL, I know that V1 minus V2 equals 12 volts. In other words, that's a KVL around this loop right here, right? If you don't see that, you say, well, 0, let's go let's go clockwise from ground back around to ground. So 0, then I go minus the plus V1 plus 12, and then I go plus to minus V2. Rearrange that guy and I get 12 equals V1 minus V2. Okay, so I take what I got from my KCLs and then I take this guy right here. Now I've got two equations and two unknowns. So what's different about a supernode is basically two things, right? With a supernode, what I have to say is I have no clear relationship between the current and voltage through this voltage source. So whatever current enters into this voltage source must flow out into whatever branches are connected on the other side. So what I do is I combine the KCL equations at the two nodes that connect this floating voltage source. Okay, so that's what I did. And then what I have to do is I have to use an an extra KVL equation to say what's the relationship between that floating voltage source and the two node voltages that it connects. Okay. So if I take that system of equations, now for me what I do is I put that into MATLAB. Okay, so here's the equation I wrote. All right, so you can see, move this off to the side. All right, so I have 1 over 2,000 plus 1 over 1,000 is one term in my matrix. And then I have 1 over 2,000 plus 1 over 1,000 is another entry. And I have a semicolon to put me on another line. And then I have 1, then minus 1. Okay. So this top row is basically the first equation over here. And this second row is this V1 minus V2. Now the way I write this is I say, remember this guy is AX equals B. All right, that B matrix is 0 and 12, like that. In other words, I'm putting this equation on the top row, and I'm putting this equation on the bottom row. All right, so this whole thing is basically A times, so X is equal to V1, V2, that's equal to 0, 12, like that. Okay. And my A is this guy right here. So if I run this, let's see what X equals. Okay, so X equals 6 and minus 6. So that tells me that V1 is equal to 6 volts and V2 is equal to minus 6 volts. Okay. Now back to my picture up here, V2 was equal to the open circuit voltage that I wanted to get. Okay. So essentially, in the way that I was trying to look at this thing, remember what I did originally was I broke this circuit up. I broke this circuit at this terminal AB. All right, and what I've found is when I'm trying to figure out the equivalent circuit for everything to the left, the open circuit voltage that I see is apparently negative 6 volts. Okay. All right, so I know that now my VOC is equal to negative 6 volts. All right. Important things in terms of the supernode analysis was I needed this additional KVL, right, to say how that floating voltage source relates to the nodes. And the other piece was I said that whatever current enters the voltage source must leave it and go into the branches on the other side. So I combined the KCL equation at this node with the KCL equation at this node. And that's no matter what. If I have supernodes, that's what I always do. Okay. Now, I need to figure out, if I want to follow with this Thevenin equivalent analysis, all right, I had, let's go back to the circuit, 2000 IX, and then I had a 1K ohm and a 2K ohm, and I got my 12 volts, and then I've got another 2K, and we called this guy IX. Now what I want to do is figure out what's the equivalent resistance looking into these terminals AB. So in my other video what I talked about is I said, well, the whole idea of a Thevenin equivalent is I want to get some circuit that represents this network, right, which consists only of a voltage source and a resistance, and must have the same IV characteristics. The IV characteristic I know ultimately is going to look like this. So this line is basically the only set of voltages and currents I can ever see at those terminals. And so in that video, kind of what I showed is, okay, if this is VOC, this is ISC, this slope right here is negative RTH. And what we find is that negative RTH is equal to negative VOC over I short circuit. Okay? So in other words, RTH is always equal to VOC divided by I short circuit. So the simplest thing in this particular case is to figure out I short circuit to figure out R-Thevenin. Now why do I do it that way and not just say, well, what's the resistance that I see looking into this circuit in that direction? Well, the reason is because I've got a dependent source inside here. And when I have a dependent source inside here, right, it makes it sort of complicated to figure out, well, if I have a load connected to this guy, a load connected to this circuit, it's a little hard to figure out exactly where his current will flow inside this network. Anytime I have dependent sources, this is the easiest way to do it. Okay, so let's try that. Let's put this guy here so that V equals 0 and my I is a short circuit current. Okay. If I have a short circuit here by KVL around this loop right here, right, it has to be the case that since V equals 0, right, it has to be the case that IX times 2000 is equal to 0. So IX has to be 0. IX equals 0 in this particular case, then what that means is that this dependent source becomes shorted, and the whole network now simplifies to a 1K ohm resistor and a 2K ohm resistor with a 12 volt source here, 12 volts, and a short circuit right here. Okay. All right, now if I want to figure out the current here, all right, so if I want to figure out what that ISC is, I can see that ISC needs to be the negative of 12 divided by 1K ohm in parallel with 2K ohms. Okay. Parallel with 2K ohms. Okay. Now why is it the opposite of that? Because whatever current is going to flow, if I have the voltage source set up like this, there's a current that's going to flow out of this guy. So he's going to split through these two and then recombine here, but he's going to be flowing in the opposite direction as I've defined I short circuit. So in this case, if I do this, 1K in parallel with 2K, if you do the analysis, is 666.667 ohms. All right. And so if I do that math, what do I find? I get 12 divided by 666.67. All right, so I find that this current is 0.018 amps. All right, with a negative there. Okay. All right. So if I look at this guy, I see that my R-Thevenin equals VOC divided by ISC. And VOC, I said, was negative 6 volts. My ISC was negative 0.018 amps. And so my R-Thevenin is 6 divided by 0.018. If I look at that, that's basically 333.3 ohms. Okay, so what I've said now is that this guy is negative 6 volts. Well, I gotta be careful about this, right? The way this thing is set up, you write it that way. My VOC is negative 6 volts. My R-Thevenin is 333.33 ohms. And then if I go back up to the original circuit, all right, what I have done is I have represented everything to the left here as an equivalent circuit. So that equivalent circuit has the same IV characteristics at this terminal AB as all of this stuff in here. So now I'm going to strap this 1K and 1K, and I want to figure out the voltage across that 1K. Alright, so here's a 1K here. Here's a 1K here. Alright, and we're told to find VO. In this case, simplest thing to do is use a voltage divider. So I say that VO equals 1000 divided by 333.33 plus 1000 plus 1000, alright, times -6 volts. Okay, so 1000 divided by 333.33 plus 1000 times -6, and I get that this is -2.57 volts across there. Okay. All right. So sort of a couple of important concepts underway in this particular analysis. One is, okay, how to break up a network like this. In other words, how to break a network at a set of terminals and replace it with a Thevenin equivalent. And again, watch the video on Thevenins if you want to understand why that makes sense. But basically what you're saying is I can always say that two circuits are equivalent if from their terminals they have the same IV characteristics. Okay? And then this idea of the supernode. Right? So when I have a supernode, the problem is I have a voltage source between two nodes and I have no way to define a relationship between the voltage across that voltage source and the current through it. So what I can do is I can write a KVL equation like I did here. I can write a KVL equation to relate, expand this guy out. I can write a KVL equation to relate the node voltages to the voltage between them, right? And I can combine the KCL at this node with the KCL at this node. And the reason I can do that is because whatever current enters here into the voltage source plus terminal has to leave it at the voltage source minus terminal and go into this branch and this branch. Okay? So I combine these two KCLs to do that and add an additional KVL relationship. That's all it really takes to solve a supernode problem. All right, so there's a lot going on in this particular problem, but it's a good example of how you can combine all the different techniques.